Hi, everyone. I'm Mingrui Zhang from the University of Washington. I'm here to present the text entry throughput, which is a metric towards unifying the speed and accuracy. This work is done by me, Shumin Zhai from Google, and my advisor, Wobbrock from University of Washington. So everybody types, but do you know how well do we type? There are mainly two factors for text entry evaluation. The first one is speed. The second one is accuracy. However, using two metrics can cause problems. For example, if we have one person using the same text entry input method, if he types in a hurry, he might type faster, but with more errors than if he types carefully, because of the existence of speed-accuracy trade-off. Then how do we evaluate the performance of the person or the method? More importantly, how do we overcome the effect of speed-accuracy trade-off? The solution I'm presenting today is called text entry throughput, which is an information level overall performance metric that combines the information of speed and accuracy. And importantly, it is a character level metric. So we are not the first one come up with this concept. Throughput in pointing is already being proposed for measuring the pointing devices. And for example, in a target aiming pointing task, if you move fast, the landing point around the target will be wider, the distribution, than if you move slowly. However, using throughput, the performance will be more consistent. For example, this is the diagram of the mouth throughput. The x-axis is the different speed accuracy condition, and the y-axis is the throughput. And we can see it performs consistently across different conditions. And we also want to have a similar effect to text entry. So let's look into text entry throughput. Before we go forward, I want to warn that there will be a lot of math content, and please don't fall asleep. So things started at one day. My advisor asked me about this throughput project, and I accepted without hesitation. So he advised me into the Shannon's information theory. And in Shannon's paper, there is such a diagram illustrating the system of a communication system. The information is getting transmitted from the source to the destination through the channel. And in a very common text entry evaluation task, we are shown with the presented string, and we type it with the input method to the transcribed string. So if we think about it, it's actually an example of the information transmission process. We can map the presented string to the source and map the transcribed string to the destination. And we humans are using the text entry method to typing and transmitting the information from the source to the destination. But during this procedure, there is noise because we can make errors. And if we can figure out what is the information transmission rate of the middle part, we are likely to get the throughput. So in text entry, the information we are transmitting is discrete because we are typing letters. It can be letters of any language. And we are making errors. So Shannon called this type of channel the discrete channel with noise. And he has a perfect example in his paper of how to calculate the throughput. So the example goes like this. Suppose there is a source X who is transmitting two symbols, 0 and 1, at a rate of 1,000 symbols per second to the destination Y. And during the procedure, there is a 0.01 error rate. So how do we calculate the throughput? Before we go into further detail, I want to first define the information or entropy. It is represented by H, so the information of X is HX. It is calculated by, for every event I, the probability of I multiplied by the log probability. And we then negatively sum them together. So in this example, there are two events, sending 0 or sending 1. So the whole information of the source is 1 bit. And Shannon told us the way to calculate the throughput is to get the mutual information, which is represented by IXY. So here is the information amount of the source, HX. And this circle is the information amount of the destination, Y. And their intersection is the common information they both have. It's called the mutual information. And the way to calculate it is using the source information, subtract the information that X has but Y doesn't. So it's this part. Okay. And now we introduce the source information, HX. We are going to look at the second part. So I'm just copying the formula from the last page. Here, the I and J in the formula represent the source and receive symbols, which can be both 0 or 1. And Pij in this formula means the probability of sending I and receiving J. For example, P11 means the probability of sending 1 and also receiving 1. Because there is an error rate, so it's 0.99. And Pji means the probability of sending I given J is received. So P10 means if I received 1, the probability of sending 0 is 0.01. And with that, we can calculate the mutual information and then further calculate the throughput. And all we need are these three factors. In text entry procedure, Pi means the character distribution in the present string, and Pij can be calculated by using Pi and the probability of typing I into J, which is this part. Let me show you here. And then Pji, we can just use the Bayesian theorem to get it if we have Pij. And all these factors can be calculated through the log from the text. However, there's a problem. The previous model is perfect for substitution error, which means you type a character into another one. However, in real life, we have omission and insertion errors. In these two situations, if you want to calculate the Pij, there's really no such a I or J in the formula. And it is solved by introducing a now character. The now character is just a placeholder character for representing the two errors. So now it becomes each character to each character. And this is a definition of throughput, and all we need are the time, the character distribution, and the transmission probability of typing I into J. However, it is still not really ready to use. There are two practical issues for throughput. The first one is Pi, the character distribution, can be different using different phrase sets. For example, here we have two phrase sets, but the character distribution of E is different, right? However, we want them to be the same, because if it's different, somebody can cheat by using a fine-tuned phrase set to increase the HX, the source information, and thus increase the throughput without even improving the text entry procedure. So our practical solution is to use the letter frequency of the target language. And in this way, we fix the HX, and also it represents the real usage of the language. And we use the English letter distribution in our paper. And if we have a closer look Here are the 3 top characters. And we won't include the now character in the source information, just to fix it. The second issue is the transmission probability, typing I into J. So think about it. If we want to calculate the throughput, we have to get the probability of typing each possible character into each possible character, right? But that would just be too many observations. For example, a person might type 100 or 1,000 of phrases to happen typing A into B. And that's just not realistic. So the way we are offering is to use the overall probability of each type to represent a single instance. For example, we can use the overall substitution probability to represent typing each character into another one. The downside, however, is those practical issues make throughput no longer a theoretical justified solution. But don't panic. Let's look how it performs in the real setting. There are 5 speed accuracy conditions in our experiment, from extremely accurate to extremely fast. And we designed a game-like experience to reach those 5 conditions. The way is to reward points for each phrase they typed. And we gave 5 minutes for each condition. And in every condition, the points for each phrase decreases from the accurate to the fast conditions. And the restrictions of error also become looser from accurate to fast. And this ensures the participants can adjust their speed accuracy strategy to reach the higher scores. Okay, let's look at the test interface. Here is the presented string here, and you can type here to finish the task. And if you type correctly, you will hear a cheating means you get money. And then if you type with some error, you will get no score. And if you type with more error, you will lose score. So we did the experiment on laptop keyboard and also mobile phone. And we are going to introduce the laptop results. If you want the full result, please refer to our paper. We mainly looked into 4 factors: the uncorrected error rate, the row speed, the adjust speed, and the throughput. The adjust speed is to compensate the row speed with the error term. So here is the result, and let's have a deeper look. The error rate and the speed all increases significantly from accurate to fast conditions. And the other metric are similar across different conditions, but we can see that throughput is the most consistent metric. And we also did analysis on these 4 metrics. We used coefficient variation to measure the variation across different conditions. And we used non-parametric analysis to measure the difference between different conditions. And we also used bootstrapping to measure the similarity between different conditions. And all the results indicate that throughput is the most consistent measurement across different conditions. And to conclude, we gained a performance metric based on the information theory, and it is robust to speed accuracy trade-offs. And we expect that researchers in text entry can report the throughput together with speed and accuracy in their future studies. However, there's also space for practical solutions. How can we make it more theoretically sound? And we also open source our throughput calculation and also our text test platform on GitHub. And especially thank Baidu company for funding. And thank you.
Thank you, Harry. We have still time for one or two questions. Are there questions? Yes.
Hello, Michel Baudouin-Lafont, Université Paris-Sud. Thank you, it's very interesting work. I have a bit of a problem with your slide that says, don't panic. You know, we're taking liberties with the theory here, but our results are good, so forget about theory. But more to the point, you seem to have an hypothesis that throughput should be constant. And in a sense, it's your measure of success. You said, look, our measure of throughput is constant, so it's better than the other measures, and it works. But on what basis can you say that human throughput in this type of condition should be constant?
Thank you for the question. So the question is, although our metric works practically, can we say that it is real consistent, like in the real life? It should be consistent. This metric, the purpose of this metric is to overcome the speed accuracy trade-off. So if you evaluate somebody typing, he has to have a speed accuracy condition, and which can influence his performance. And our target is to get a performance level metric. So even it's not, like I said, theoretically justified, we have to make trade-off between theory and practical. For example, like I said, there are problems if you strict on the theoretically sound definition. You have two practical issues. So that's like you have to get some trade-off to make it work and to make it usable and to make it easy to calculate, and also the result is sound. Thank you.
Okay, we have still time for one question.
Okay. Yves Guillard, University Paris-Sud.
Sorry, could you raise up your voice?
Okay, so
thank you.
Okay. There seems to be a presupposition in this work which I think is worth discussing. The idea is that you unify speed and accuracy using the TP. Unification, the word you use, okay? And so it sounds like it's better to have one descriptor of performance rather than two. But my feeling is that the performance in typing, for example, is inherently two-dimensional. It really has two dimensions, speed and accuracy. So if you get one score, you lose some information, okay? So the penultimate slide recognizes this, but the title suggests that with the TP you solve a problem. In fact, you get a half. You describe half of the performance. Do you agree with that?
Thank you. So the question is, if we unify the speed accuracy, we actually decrease the one dimension of the performance, because the performance is essentially two dimensions. So our purpose is not to substitute the speed or accuracy. Our purpose is to have a single measure to enable cross-publication comparison, cross-device comparison, and to make it handy for further research to compare with prior works. I would take a not very suitable metaphor to think about F1 score in machine learning. Like they derived the F1 score from recall and the precision, but F1 score does not show the information of those two measures. However, it is an overall performance. So, and also people use that to compare different works. So that's like the more practical point of view of the throughput. And also, more importantly, it overcomes the speed accuracy condition. Thank you.
Okay, thank you, Ray.